So, we've seen the challenges. Now let's look at the solution, the query decomposition workflow. This process breaks down complex questions into simpler, independent subqueries, making retrieval much more effective. Consider this example. Compare maintenance costs of Permian Basin assets against Eagle Ford Shale for Q3 and identify which region had higher downtime. This single query actually contains three distinct intents: a cost comparison, a downtime analysis, and a direct comparison between regions. A naive system would struggle to address all of these effectively. When you try to represent a multi-intent query with a single embedding, you dilute its meaning. This makes it very difficult for the system to retrieve the correct information for any of the intents, leading to retrieval failures. For a naive search system, this dilution means the semantic representation of the query is weak. Consequently, the top search results might only address one of the intents, leaving the others unfulfilled. This ultimately leads to incomplete or even hallucinated responses because the system doesn't have the full picture. Now that we understand the workflow, let's explore how to implement query decomposition, specifically using a compound query retriever. Query decomposition is essentially the process of transforming a complex, compound query into a set of atomic or single-intent subqueries. This allows each subquery to be executed independently, treating what looks like a single request as a multi-step retrieval task. This workflow typically follows a three-stage logic. First, classification. The system determines if the query is indeed compound and needs breaking down. Second, decomposition. If it's compound, the system generates n distinct subqueries. Finally, fusion. After retrieving results for each subquery, these results are combined into a coherent context for the final answer. We've covered how to break down queries. Now, we need to talk about how to effectively combine the results from those separate subqueries. Simply concatenating them can lead to problems. The compound query retriever is a key component here. It extends the functionality of a query fusion retriever and crucially uses a large language model, or LLM, to trigger the decomposition logic. This approach prevents unnecessary overhead for simple queries that don't need decomposition. The first step in the decomposition process is query classification. This is handled by a method that checks if the query is compound. It relies on a carefully crafted prompt sent to the LLM, asking it to classify whether the input query is simple or compound. Once a query is identified as compound, the next step is subquery generation. This is managed by a _decompose_query method. It uses another structured prompt, often designed to return a JSON output, to generate distinct subqueries. You can also control the maximum number of subqueries generated through a parameter like num_queries. Here's a look at the Python code for these two key methods. The underscore is _compound_query function sends the query to an LLM using a classification prompt and checks if the response indicates yes. The _decompose_query function does similarly, but uses a different prompt designed to generate subqueries, which are then parsed from the LLM's text response. Finally, let's wrap up by discussing the operational aspects and integration of query decomposition. This involves understanding the trade-offs and how to integrate these systems effectively. Simply concatenating results from multiple subqueries isn't ideal. It often leads to redundant information and inconsistent relevance scores, making it hard to present a clear, consolidated answer. A powerful technique for merging these results is reciprocal rank fusion, or RRF. It's the production default for a reason. It calculates a score for each document based on its rank across all the subqueries. The formula, score D equals sum of 1/k plus rank of D for query Q, effectively balances documents that appear consistently across different queries, giving them a higher overall score. Beyond RRF, there are other fusion modes to consider. Relative score fusion normalizes scores from different query sets onto a 0 to 1 scale, which is useful when your subqueries might have very different scoring distributions. Then there's distribution-based score fusion, which accounts for the mean and standard deviation of scores within each result set for a more nuanced combination. In terms of system integration, the Query Engine Manager acts as a crucial factory for retrieval components. It's responsible for initializing various components, including post-processors like re-ranking and similarity filtering, and it wraps these retrievers to ensure the quality of the fused results before they're injected into the LLM's context. So, to summarize the key takeaways, query decomposition is vital for handling multi-intent enterprise queries. The classification step is critical for optimizing latency by skipping decomposition for simple queries. RRF is an excellent choice for merging results effectively without needing complex score calibration. And finally, post-processing steps like re-ranking and similarity filtering are essential to prevent noise from overwhelming the context window. This section has highlighted the core components and considerations for implementing query decomposition, from classifying complex queries to fusing their results. The trade-offs are manageable with careful design and integration. This code snippet illustrates the Query Engine Manager's build method. You can see it first initializes post-processors like similarity post-processor and a re-ranker. Then, it configures the compound query retriever, specifying prompts, post-processors, and importantly, setting the fusion mode to reciprocal_re-rank to leverage RRF for robust result merging.